Welcome back to Greenplum 2020, the reimagined digital customer conference. My name is Jacques Eistock. Our next guests are Ashka and Francisco. They're here to deep dive into PXF. This is the query federation engine for the modern enterprise. So Ashka, could you tell us a little more about this fantastic add-on capability for Greenplum, please?
Yeah, of course. Thank you so much for the introduction. As he mentioned, my name's Ashka and my co-speaker today is Francisco. We're both engineers working on the Greenplum Managed Data team here at VMware. We'll be covering PXF, the Greenplum Query Federation engine for the modern enterprise. So this talk will be broken down into a few key components. First, we'll be talking about the problem that we see in the industry and how PXF can address them. And then we'll be talking about PXF architecture and performance. So what do we see in the industry? Say that you have a data specialist running on Greenplum and they ask the following question. How can I run an analytical workload consuming semi-structured and structured data from external data sources stored in different file formats within Greenplum? The answer to that question is PXF, otherwise known as the Platform Extension Framework. Greenplum uses PXF as a federated query engine to access external heterogeneous data. It allows Greenplum users to connect to quite a few different external sources, including Oracle, Hadoop, Azure, GCP, Amazon Web Services, just to name a few. So how does PXF allow users to connect to these sources? Well, we offer native connectors depending on the source. For example, different relational databases such as SQL Server, DB2, MySQL can connect to Greenplum using our JDBC connector. File systems that are compatible with Hadoop, such as S3, Azure, Aliyun, and more, can connect through the Hadoop-compatible file system API. We also have Hive and HBase connectors, and our last connector is a specialized connector for AWS called S3 Select, which Francisco will talk more about later in the presentation. So let's now provide like a typical user experience. Users usually connect to Hadoop or Hive as a starting point. For both of these cases, we connect to PXF through a single server configuration. And connections with PXF can be done with enterprise-grade authentication, such as Kerberos, and can support accessing multiple Hadoop clusters within a single Greenplum installation. In Greenplum, external tables only store the metadata in the catalog. The data itself resides outside of Greenplum. So we can create connections to our external data sitting on Hadoop by creating an external table in Greenplum. So let's say that we want to run an annual report on some cold data in our Hadoop cluster. We can access it first by creating the PXF extension, then create an external table where we specify some key elements. So if you take a look here at location, it contains the information about the protocol, PXF, and three components: the data's location, format, and external server configuration. The location, circled in blue, is the path to where the data actually sits in Hadoop. And in red is the profile, which tells us the type of data. So in this case, we have HDFS Parquet. Finally, in green, we dictate our server, which is how we access the data and handle our authentication requirements. Once the external table is created, from the user's perspective, you can treat this as any other table in the database. You can query it, you can join it with other tables, etc. So as users start consuming data from Hadoop, it's very likely that they want to start accessing other databases. The most common ones that we see are Oracle, DB2, and SQL Server. And users will begin to add more use cases to PXF. So typically we see one or more database clusters are federated through PXF on Greenplum. So in our example, now that we have Hadoop up and running, we also want to connect to an Oracle cluster, and we can do this through PXF's native JDBC connector. So much like the way that we access external data in Hadoop, we access external data in Oracle in the same manner. We just change the three parts in our location when we create an external table. So in the case of JDBC, we give the table name in Oracle as the path, and we update the profile and server accordingly to have the correct information that we need. So you may notice that we no longer need to create the extension here. Regardless of how many external data sources we connect to PXF, we'll only need to instantiate the PXF extension once. So more and more, we see enterprises moving data to the cloud due to availability, durability, costs, etc. And with PXF, we can access all of these different servers concurrently. So let's say in our user's case, we had a different team come by and they wanted to connect to their data, which resides on S3. It's possible for PXF to create connections to the database to an external data source for a different team within the same enterprise with different configurations. So let's say an enterprise is moving their cloud data from AWS to Azure. In Greenplum, it's very easy to do this move. PXF is cloud agnostic, so we can seamlessly transition between clouds when we're in this situation. All you have to do is drop the old table and recreate it with the newly updated location. This action is really fast and efficient because the data sits outside of Greenplum. So really the only information that you're changing is the metadata that's stored in the catalog on where to access our external data. PXF's ability to store and query data from the cloud allows us to decouple computation and storage. So let's go back to our problem statement. We had a data specialist who wanted to run analytical data from external sources inside Greenplum. They can now do so by provisioning an ephemeral Greenplum cluster on top of Kubernetes and use PXF to connect to their external data already living in the cloud. They have the ability to size the cluster depending on the workload and can destroy it at will once the workload completes. So PXF with an ephemeral Greenplum cluster on Kubernetes allows enterprises to have on-demand data warehouses. Now I'll hand it over to Francisco, who will talk about the PXF architecture and performance.
Thank you, Ashka, for that amazing high-level overview of PXF. Now, let me go more in depth and talk about the internals of PXF. I will be talking about the PXF architecture and some of the performance benefits that PXF offers. So in a typical installation of PXF, PXF lives alongside with Greenplum, meaning that PXF will be installed on the Greenplum master and every segment host. PXF itself has 3 components, but today I will be talking about 2 components, the PXF extension and the PXF server. So the PXF extension is installed and runs on every segment. As we can see here in this diagram, in the teal box inside every segment, we have the PXF extension. And it lives inside the Greenplum process, and it is the component that interacts between Greenplum and the PXF server. The second component is the PXF server. So the PXF server is a stateless Java virtual machine which uses Tomcat as the container. The PXF server is started on every segment host. In this diagram, we have 2 segment hosts, and therefore we have 2 PXF servers. Typically, a user query originates on some client. It can be pSQL, dbeaver, or some other application interacting with Greenplum master. The query is then dispatched by Greenplum master to all segments. The PXF extension running on every segment will then interact with the PXF server using the REST API endpoints. Let's take a deeper look into this process. So PXF can read and write data from external data sources. Let's focus on the read case first. Let's say we have a table. Let's call it my table on Hadoop. So we issue a query, select star from my table on Hadoop. So Greenplum master dispatches the query to all 6 segments. Every segment opens a connection to the PXF server. PXF is a multi-threaded application and will handle each connection on its own thread. PXF will gather metadata from the external system. For example, if we are querying data from Parquet, stored in my Hadoop cluster, PXF will then gather the list of Parquet files. And for large Parquet files, it would split these files. It will then assign a list of files or splits for each segment to work on. So this effectively distributes the workload among all the segments in the Greenplum cluster. Each segment gets a unique list of files or splits, and then each segment will iterate through the list of splits it will process, pulling data in parallel from the external system. And PXF will transform the Parquet data in this example to tuples that can be consumed by Greenplum. For the write case, every segment will open a connection to the PXF server, and it will write data for that specific segment. All segments write data to PXF in parallel. So PXF is able to take advantage of the parallel aspects of Greenplum, and it allows us to have performance gains in PXF, as we can see in this graph. So this is an experiment I ran a while ago. For the experiment, we use the JDBC connector. In the experiment, we have 2 Greenplum clusters. And the experiment consists of transferring 50 gigs of data from one cluster to the other. Each cluster has 28 segments, 7 segment hosts, and master. So the experiment compares a query that runs on a single thread versus running the same query on a parallel, taking advantage of parallel aspects of PXF. So both queries use PXF, but in the second query, we just add 3 properties in the table definition, as we can see in this graph and this DDL. And that makes the query run in parallel. So the 3 properties are highlighted in red: partition by, range, and interval. And partition by specifies the column name to use for the partitioning on the external system, as well as the partition type. We support int, enum, and date partition types. The range property specifies the range of values for the partition, and the interval specifies the step in the data range. By adding these 3 properties, we enable parallel querying on the external system for this table. In the experiment, we partition the data by GP segment ID, which is a special column in Greenplum. PXF internally will create 28 scans to the external system, and each scan will contain a where clause, for example, where GP segment ID equals 0, GP segment ID equals 1, and so on. So with this feature, we see a 7x speed up gain going from 70 minutes down to 11 minutes. And for the end user, they query the table the same, exactly the same as before, but PXF makes the query execute faster. So another performance benefit in PXF is the support for pushing predicates. In this example, where we query from the orders table, and we filter the data by the state of CA. So the predicate corresponds to the where state equals CA portion. When the user issues this query, the predicate information is passed from the segments to PXF. PXF then in turn passes the predicate information to the external database. In this case, we have a MySQL database. MySQL will then only return data matching the state of CA, as opposed to doing a full fetch of the external data. And the filtering happens at the external system and not inside Greenplum. In this table, we see predicate pushdown supporting PXF. Depending on the external system, PXF will either push the predicates to the external system, or PXF can also do filtering internally. In the case of JDBC and S3 select, PXF will push the filtering to the external system. In the case of Hive, PXF can do partition pruning for partition tables, reducing the amount of scan files. But PXF can also apply filters at the PXF level for some data formats. For HDFS, S3, Google Cloud Storage, and the cloud connectors in general, PXF also applies filters at the PXF server for the Predicate format. And this reduces the CPU and memory footprint. And let's take a look at the results of some experiment that we run. So we run an experiment that compares regular S3 access versus using the S3 select feature. S3 is using the Hadoop compatible file system API, whereas the S3 select is going through the S3 select API. The S3 select API allows us to push predicates for some data formats, for example, CSV, Parquet, and JSON. And S3 select itself will do the filtering and return only the matching tuples. This reduces the amount of data being transferred from S3 to Greenplum. With larger data sets, we can see that the benefit is greater. In the green line, we can see that scanning 3 terabytes of data with a predicate takes a little less than 10 minutes, whereas doing a filtering inside Greenplum forces us to transfer the entire data set, and then the filtering happens at Greenplum. And this query takes a lot longer, a little under 40 minutes to complete. So S3 select is 4 times faster than the regular S3 access when accessing 3 terabytes of data. So another performance benefit that PXF offers is column projection. With column projection, only the columns that we need in the query are transferred back from PXF to Greenplum. In the example above, columns item, amount, and state are the projected columns. So when accessing data from Hive, PXF will read the projected columns and stream back only the subset of columns that we need. This feature helps us reduce network I/O as well as disk I/O in some cases. For example, when reading ORC files, where the file format is optimized for columnar storage. So this table shows column projection support. We have column projection for all the native connectors except for HBase. For JDBC and S3 Select, PXF will only query the projected columns to the external system, reducing the amount of data that we transfer from the external database, as well as improving the disk I/O in some cases. For Hadoop and Cloud connectors, PXF supports column projection for the Parquet file format, which offers I/O benefits when running inside of PXF. For Hive, PXF offers column projection for all data types. So in summary, Greenplum offers the ability to query data from external sources, making it transparent for users querying this data in different formats, in different data locations and systems. And PXF offers multiple performance benefits like parallel high throughput data access, column projection, and predicate pushdown. PXF allows you to read and write data to external sources. It offers native connectors out of the box, and it is a pluggable framework, meaning that you can write your own connector geared towards your own use case. And finally, PXF is open source. So PXF is the federation engine for the modern enterprise. Thank you so much for listening to our presentation, and feel free to reach out to us for more information. Thank you.
Thank you so much, Francisco. Thank you, Ashka. I literally can't say enough good things about PXF and the capabilities of being able to, simply and scalably and multifacetedly reach out and pull all of this data into one common query engine. So I can use the same interface, the same languages, the same SQL, regardless of where my data is and regardless of where I actually install Greenplum itself. So thanks again for that talk.